In this video, we'll learn about IR spectroscopy. We'll study basics and we'll see how the spectroscopy works. Towards end of the video, we will learn how to interpret the IR spectra. The electromagnetic spectrum covers electromagnetic waves with the frequencies range from 1 Hz to 10 power 20 to 23 Hz, and the wavelengths corresponding to thousands of kilometers to a fraction of size of an atomic nucleus. In most of the frequency bands above, a technique called spectroscopy can be used to physically separate waves of different frequencies, producing a spectrum showing the constituent frequencies. And the spectroscopy is used to study the interaction of electromagnetic waves with the matter. What is IR spectroscopy? IR spectroscopy, rather called vibrational spectroscopy, involves the interaction of infrared radiation with the matter. And spectroscopy it's a branch of science that deals with the spectra provided by molecules when molecule interacts with the energy. Here the energy is given by electromagnetic radiation to the molecule. And from this, on the spectra, we'll see spectral lines, or we call absorption lines. And the position of the absorption lines depends on the types of functional groups present. And the IR spectrum is a unique fingerprint of the entire molecule. The infrared portion of the electromagnetic spectrum that what we use for IR spectroscopy, and it's usually divided into three regions: the near, mid and far infrared, named for their relation to the visible spectrum. The higher energy near IR, approximately 13,000 to 4,000 centimeter inverse, and it can excite, overtone or combination modes of molecular vibrations. The mid IR, approximately 4,000 to 400 centimeters inverse, is generally what we use for IR spectroscopy, and we use this to study the fundamental vibrational and associated rotational vibrational structure. The far infrared, approximately 400 to 30 centimeters inverse, has low energy and may be used for rotational spectroscopy and low frequency vibrations. For the spectroscopy, we use mid IR region radiation and the frequency ranging from 400 centimeter inverse to 4,000 centimeter inverse. The mid IR region categorized into two groups. One is functional group region. The functional group region contains relatively few peaks. These are typically associated with the stretching vibrations of functional group. Fingerprint region usually contains many peaks, making it difficult to identify individual peaks. However, the fingerprint region of given compound is unique and therefore can be used to distinguish between compounds. We can see one of the IR instrument in the picture, and the graph represents here how the infrared light passes through the sample, and the transmitted light detected by the detector The detector compares the incident light and the transmitted light, and it plots the data on the monitor, which displays as a spectrum. The band intensities is expressed as the units of absorbance or transmittance on the y-axis. Absorbance is a reciprocal of transmittance, as we can see from the formula. The spectra here is IR spectrum of octane, but on the left side is percentage of transmission on y-axis, on the right side absorbance on the y-axis. In both cases the spectral data is same, but the spectra looks like flipped upside down. So how the IR spectroscopy works? We know energy of any molecule is sum of energies by translational, rotational, vibrational, electronic and nuclear orientation of molecule. The table here shows how different electromagnetic radiations are responsible for different energy transitions within a molecule. Since we are using infrared light, it causes molecular vibrations in the molecule. And this is the reason why IR spectra are also called vibrational spectra. There are two types of molecular vibrations, stretching and bending. The stretchings or bendings are either symmetrical or asymmetrical. As you can see here, the stretchings involves change in bond lengths between the two atoms, and the vibration involves change in bond angle between two atoms. Here we can see stretching and bending vibrations of CH2. These two structures on the left side represents symmetric and asymmetric stretch of two hydrogens on CH2. The symmetric stretch has wave number 2853, while the symmetric stretch have wave number 2926. On the four structures on the right side represents bending vibrations, and these two are in-plane vibrations on the extreme right two. These two are out of the plane vibrations. From the wave number we can see they have different vibrational frequencies. So what we need to understand is the vibrational band of any functional group appears at characteristic wave number. Entire IR spectrum may be used as a unique fingerprint of a compound. Each functional group has unique fingerprint region. So the number of spectral lines of any molecule in the spectrum depends on the number of vibrations. So the number of vibrations is given by degree of freedom. For nonlinear molecule, degree of freedom is 3n minus 6. For linear molecule, the degree of freedom is 3n minus 5. Here the n represents number of molecule. For example, propane, which is molecular formula C3H8, which is non-linear molecule. So the degree of freedom is 3n minus 6, and it has 27 fundamental vibrations. Therefore, we might see 27 bands in the IR spectrum. This is the example of stretching and bending vibrations of water molecule H2O. and also stretching and bending vibrations of molecule CO2. The vibrational energies of different functional groups can be explained by Hooke's law. The frequency of the vibration between two atoms depends both on strength of the bond between them and on their atomic weight. So stronger the chemical bond, shorter the distance, and larger the vibrational frequencies. As we can see, carbon-carbon triple bond is shorter than carbon-carbon single bond. Since the shorter the chemical bond and shorter the distance, the larger the vibrational frequency. And also here the vibrational frequency for carbon and hydrogen, and then carbon and carbon. The hydrogen is comparatively smaller than carbon, so that's why it has higher vibrational frequency. If you compare carbon and chlorine and carbon and bromine, bromine is much bigger than chlorine. So since the bromine is bigger, larger the mass, smaller the vibrational frequency. These are the few methods how to do sample preparation. For solid samples, we use thin plate samples. Simply we insert sample here and then we place it in the slit of the instrument. If you have powder samples, you may have to prepare KBr pellets. For powder samples, you have to take your sample along with KBr or KCl in the mortar, and you have to grind it to fine powder and assemble the die set as shown in the drawing. And when assembling the die, add the powder to the 7 mm collar. Put the die together with the powder into quick handy press. Press the powder for 2 minutes to form a pellet. A good KBr pellet is thin and transparent. If it is not transparent, it might give a poor spectra. Also, any white spots in the pellet indicates that powder is not ground well enough or not dispersed properly in the pellet. For the liquid samples, we use highly polished salt plates as sodium chloride or silver chloride or KBr, and we sandwich the liquid with the two plates. This method is not useful for volatile liquid because the liquid might be evaporate while the spectrum is being obtained. And this method is also not recommended for any toxic or smelly liquids. Microporous polyethylene films, often called IR cards, widely used for IR analysis. They are much simpler, disposable, and we can use the compound directly by keeping on the polyethylene circular disc on the paper card, on the IR card, and we can use it for IR analysis. These cards are good enough to do the IR analysis between 400 to 4000 centimeter inverse, but if you do not subtract the spectra of the polyethylene material, we might see extra peaks at 2800 and at 2840 centimeter inverse or 2910 centimeter inverse. So how do we analyze the IR spectrum? When you have the IR spectra and the molecular formula of the compound, first you need to calculate degree of unsaturation. Degree of unsaturation is degree of unsaturation helps to identify the number of rings or number of pi bonds, or sometimes a combination of number of rings and pi bonds. The formula for degree of unsaturation is given by number of carbons minus number of hydrogens over 2 minus number of halogens over 2 plus number of nitrogens over 2 plus 1. Once you calculate degree of unsaturation, then you look for peaks in functional group region between 1300 to 4000 centimeter inverse, because there we see less number of peaks but are characteristic peaks for functional groups. If you do not see any major peaks in the functional group region, probably your compound is strictly hydrocarbon. And also it is very recommended to check the fingerprint region between 900 and 600 centimeter inverse, because that's where you see strong absorption bands for aromatics, alkyl halides, amines, amides, and for carboxylic acids. If you're really new to spectral analysis or IR spectra interpretation, you should not try to assign or study every peak from the IR spectrum. This picture here helps to how to look for different functional groups when you have an IR spectrum. Let's see how to study an IR spectrum using few examples. In this example, it's a simple hydrocarbon. The top spectrum is acyclic and the bottom spectrum is cyclic hydrocarbon. Cyclic and acyclic hydrocarbons are conformed by the different carbon-carbon vibrational frequencies. In the top spectrum, we can see two different carbon-carbon frequencies. In the bottom, we'll see on one kind of carbon-carbon vibrational frequencies, because the molecule is symmetrical. In addition to carbon-carbon frequencies, we also see sp3 carbon hydrogen vibrational frequencies, and usually the sp3 carbon hydrogen vibrational frequencies are 2900 centimeter inverse. In this example, this is hydrocarbon, and also we have unsaturation, carbon-carbon double bond. So we'll see a carbon hydrogen frequency, vibrational frequency, but it's a sp2 carbon hydrogen frequency along with sp3 carbon hydrogen frequency. sp2 carbon hydrogen frequency will be at 3000, while sp3 carbon hydrogen frequency is at 2900. Also, using IR spectrum, we can identify the cis and trans isomers. In this example here, we have cis isomer and trans isomer. The cis isomer has lesser vibrational frequency than trans. In this example, we see an aromatic molecule with a terminal alkyne. Since we do not have any sp3 carbon hydrogens, we do not see any band at 2900. The aromatic sp2 carbon hydrogen band will be at 3030 centimeter inverse. And also for terminal alkyne, C triple bond C carbon hydrogen frequency will be 3300. Also, we can see the carbon-carbon frequencies at around 1500 region. The difference in functional groups between these two molecules is sp3 sp carbon hydrogens. Here we see sp3 carbon hydrogen, In the second structure, we do not see any sp carbon hydrogen, which we do. That's why we are missing the peak at 3300, which is prominent for sp carbon hydrogen. But we still see carbon carbon, aromatic carbon carbon. This is an example of an alcohol molecule, and a broad band at 3300 and 3400 is an indication of presence of OH group. In these two examples, we see a broad band from 3200 to 3500. This example is for amine molecule. We have a carbon hydrogen sp3 carbon hydrogen bands. We have a sp3 carbon hydrogen bands at 2900. Now in these two cases we have amines, but the first example is a primary amine and the second structure is secondary amine. So for primary amines, we see a peak at 3400, but for primary amines we see splitting of a split of peak into two, but for secondary amine we don't see any split. If you see a peak at 3400 and the peak split into two, which means you have a primary amine functional group. Now we have acid, carboxylic acid molecules. We have all sp3 carbon hydrogen stretches, and also we see C double bond O stretch at around 1690, and also we see a broad band for OH. If you see a broad band along with the C double bond O stretch, you might have carboxylic acid functional group. And also carboxylic acid OH frequency will be from 2400 to 3300. This is example for acid chlorides. If you see C double bond O split into two, that could be reason because of presence of halogen next to carbonyl. So here we see C double bond O split into two, and this is due to presence of halogen next to carbonyl. And also we are not seeing any OH group up here, which means we do not have any carboxylic acid, and we have acid chloride. This is example for anhydride. We have a cyclic and linear and cyclic anhydrides. Since we have two C double bond O groups, two carbonyls, we see C double bond O will split into two, but for linear anhydrides, for linear anhydride we see a strong band on the left side. For the cyclic anhydrides, we see strong band on the right side of the split. This is example for amides. Here we have an amide molecule. So we have split for NH. So we see NH frequency around 3200, and also along with the carbonyl